Hello, young chemists. Have you ever baked cookies and noticed that the recipe says 2 cups of flour, 1 cup of sugar, and half a cup of butter? You can double it, halve it, or even triple it, but the ratio always stays the same. Chemistry works exactly like that when it comes to empirical formulas. The empirical formula is the simplest whole number ratio of atoms of each element in a compound. It's not about the exact size of the molecule, but about the proportion. For example, glucose has the molecular formula C6H12O6, but if you strip it down to the simplest ratio, it becomes CH2O. Similarly, hydrogen peroxide is H2O2, but its empirical formula is just O. So, think of the empirical formula as the chemical recipe card. It tells you the proportions, not the total serving size. Now let's get a bit more formal, or shall I say empirical. The definition of empirical formula is simple. It is determined from the percentage composition of elements. The formula goes like this. Take the percentage of each element and divide it by its atomic mass. That gives you the relative moles. Then simplify those values into the smallest whole number ratio. For example, number of moles equals mass divided by atomic mass. This way, even without knowing the exact molecular size, we can still crack the elemental proportions. And once you know the molar mass of the compound, you can take this empirical formula and extend it to the full molecular formula. So, in short, empirical is the starting clue, molecular is the complete story. Alright, let's learn the steps like a cooking recipe. Step 1. Find the percentage composition of each element in the compound. Step 2. Divide each percentage by the respective atomic mass to get relative moles. Step 3. Divide all those mole values by the smallest one. That way you normalize the ratios. Step 4. If you get fractions like 1.5, multiply everything by 2 to make them whole numbers. Step 5. Write down the simplest whole number ratio, and that's your empirical formula. Picture it like weighing ingredients for a cake. Even if you don't know how many people the cake will serve, you know the flour to sugar ratio. Same idea in chemistry. Let's test this out with water. Its composition is 11.11% hydrogen and 88.89% oxygen. Now, divide each by atomic mass. Hydrogen 11.11 divided by 1 equals 11.11. Oxygen 88.89 divided by 16 equals 5.56. The ratio comes out to roughly 2:1. That's why the empirical formula of water is H2O. Here's the fun part. In this case, the empirical and molecular formulas are the same. Water is a simple and honest fellow. What you see is what you get. But that's not always the case, as we'll see next. Now let's move to something trickier, benzene. Its percentage composition is 92.3% carbon and 7.7% hydrogen. Divide by atomic masses. Carbon 92.3 divided by 12 equals 7.69. Hydrogen 7.7 divided by 1 equals 7.7. That gives us a ratio close to 1:1. So the empirical formula is CH. But wait, the actual molecular formula of benzene is C6H6. That's 6 carbons and 6 hydrogens. So the empirical formula gave us the proportions, but not the actual count. It's like someone told you that a pizza recipe needs 1 part cheese and 1 part sauce, but didn't mention how big the pizza was. That's where molecular formula comes in to finish the picture. So, where do we use empirical formulas? Pretty much everywhere a chemist looks. In analytical chemistry, it's the first tool to identify an unknown compound. In industry, pharmaceutical companies use it to ensure drug composition is correct. Fertilizer companies use it to check nutrient content, and metallurgists use it to test ores. Organic chemists also use empirical formulas in combustion analysis. By burning a compound and measuring carbon dioxide and water produced, they work backward to find the empirical formula. It's the detective work of chemistry The empirical formula is the first clue, and molecular structure is the full case solved. Let's wrap it up with a clear summary. The empirical formula is the simplest whole number ratio of atoms in a compound. You determine it by using percentage composition, dividing by atomic mass, and simplifying the ratios. Remember, the empirical formula is not always the same as the molecular formula. Glucose simplified down to CH2O, benzene simplified down to CH, but water stayed the same. This concept is hugely important in exams and even more important in real life, from analyzing ores, salts, and fertilizers to designing medicines. Mastering empirical formulas sets the stage for calculating molecular formulas, which we'll explore next. So, to sum up, empirical formulas are like a recipe's ingredient ratio. They don't tell you the serving size, but they make sure the taste is always right. I hope this class helped you see chemistry not as abstract math, but as the real world recipe book of elements and compounds. Catch you in the next session, where we'll scale up from empirical to molecular formulas, the bigger, juicier story of stoichiometry.